Hi everyone. In this project, I worked on the home credit default risk classification task. The goal was to predict whether a loan applicant would default, where target equals 1 for default and 0 for non-default. Because this is a lending application with a highly imbalanced dataset, I treated it not only as a predictive modeling task, but also as a responsible AI problem involving fairness, reliability, and interpretability. I start with the exploratory data analysis and pre-processing. I examined class imbalance, missing values, and the distributions of important financial variables such as income, credit amount, annuity, and age-related features. Since the variables had substantial missingness, especially property-related features, I used feature-type-aware pre-processing instead of simply jogging records. I also performed feature engineering to create more meaningful predictors, including income to credit ratio, income to annuity ratio, credit to annuity ratio, and the summary statistics of the external risk scores, such as ext source mean and the mean and the max. And this three. And then we can see the mean is 0.2098081, and max is about 0.8186, and the mean is about 0.175. For modeling, okay, here is the correlation matrix. So we can see the top numeric features here. And here it is the PCA. Show the various ratio. For modeling, I compared several approaches, including regularized logistic regression, CAT-boost, LightGBM, His gradient boosting, and MLP neural network. I also compared balanced and imbalanced learning settings. This comparison showed why accuracy alone is misleading in an imbalanced credit risk problem. For example, the imbalanced logistic regression achieved high accuracy but very poor recall, while the balanced version captured many more defaulters. Based on overall discrimination and business relevance, I selected a weighted example as the final model and tuned the classification threshold using a false positive and false negative cost framework instead of the default 0.5 threshold. Now I will address the first required question: how I ensure the model aligns with responsible AI principles, and how I adjust the fairness and bias. Focus on responsible AI in three main ways: fairness auditing, reliability analysis, and careful deployment considerations. And here is the RC curve, and this is a precision report curve. Okay. So here is the II matrix. For gender, for fairness, I did not assume that good overall performance meant the model was bad. Instead, I directly evaluated subgroup performance across gender and age groups. I measured demographic parity, true positive rate, false positive rate, precision, and AUC for each subgroup. For gender, I found clear disparities. The model predicted positive outcomes of more often for males than for females, and both the true positive rate and false positive rate were also higher for males. For age groups, the disparities were even stronger. Younger groups had high positive prediction rates and higher false positive rates, while the oldest group had a very low positive prediction rate and a true positive rate close to zero. These results show that acceptable overall performance does not guarantee fairness across groups. To make the analysis more useful, I also summarized the fairness gaps across subgroups instead of only presenting row tables that help highlight where disparities were largest and where additional monitoring would be needed. Second, I examined the role of sensitive features. In the SHAP analysis, gender appeared as an influential variable, which is a concern in the lending context. Instead of ignoring this result, I treated it as a warning sign. I then connected this finding to subgroup fairness analysis and identified gender feature removal or evaluation testing as an important next mitigation step. It shows that I was not only minimizing performance, but also checking whether the model might rely on sensitive information in an ethically problematic way. Third, I evaluated model reliability through calibration analysis. I used a calibration curve and the Berea score to assess whether predicted probabilities matched observed default risk. The Berea score was about 0.135, and the results suggested that the model was not perfectly calibrated. This is important because in lending, poorly calibrated probabilities can produce overconfident or misleading risk estimates. For that reason, I would not recommend using this model as a fully automated approval or rejection system. Instead, I would position it as a decision support tool with human review, especially for borderline cases. Now I will answer the second report question. What methods are used to make the model interpretable and how does method support ethical decision making? I use several interpretability methods, with the most important being feature importance analysis, SJP, and partial dependence plots. First, I used feature importance analysis to identify which variables were driving the model most strongly. The most important predictors consistently include external risk scores and credit burden variables, such as EXT source mean, the mean and max. Good credit ratio and credit annuity ratio. These are meaningful financial risks. Risk-related features, so the model is easier to explain in a lending setting. Second, I used SHAP, which was the most important interpretability tool in this project. SHAP qualified how much each feature contributed to predictions and helped reveal the model's overall decision logic. This shows that variables such as credit ratio, EXT source mean, credit NLT ratio, and the EXT source features had strong influence on model output. More importantly, SHAP also showed that code genre was influential. This directly linked interpretability with fairness analysis. So in this project, SHAP was useful not only for explanation but also for identifying ethical sensitive model behavior. Instead, I used partial dependence plots to understand how predicted default risk changes as important variables change. This helped me verify whether the model respond to key financial variables in a reasonable and interpretable way. In other words, PDPs helps check whether the learned relationships were economically plausible rather than arbitrary. This interpretability method supports ethical decision-making in three ways. First, they improved transparency by showing which variables drive predictions. Second, they helped detect possible reliance on sensitive or proxy features. Third, they make it easier to justify why a model output should be reviewed by humans rather than followed blindly. In a credit risk setting, this is especially important because model predictions can directly affect people's access to financial services. To conclude, this project was not only about maximizing predictive performance, a beautiful flow that combined predictive modeling with responsible AI evaluation, including fairness auditing, calibration analysis, and interpretability. The final example achieved reasonable discrimination, but more importantly, the analysis showed that the model still has fairness gaps and calibration limitations. There. So much for my video. Thank you.